Hello students, this is our Chapter 4 video notes for Chemistry 1510. In this video we are going to look at electrolytes and solubility. So when we start talking about electrolytes, we really need a little bit of background information because you've probably heard of electrolytes before and you've probably heard of them with respect to Gatorade. So let's talk about what it looks like when things dissolve in water. So when something dissolves in water, it means that the water is kind of surrounding the molecules or ions, right, depending upon what's being dissolved, and it kind of traps them individually. And we actually have a word for this. It's called a solvent cage, which just sounds crazy if you're not a chemist. So the water surrounds the molecules and the ions. It can kind of an individual fashion. So I don't know, it's really hard for me not to write solvent cage. So maybe I'll kind of show you what I mean when I say a solvent cage. So let's come over here to the dissociation or the dissolution of an ionic compound. You see this positive here that I'm highlighting? These positives that I'm highlighting are surrounded by these water molecules, and that's what is kind of making that thing that we call a solvent cage. So the water is surrounding those molecules or ions, and it's breaking the attractions between the ions or molecules. And then look over here where we have this negative charge in the ionic compound. And then notice how, again, the water molecules are surrounding that. But this is really interesting. Let's look at the water molecule around the positive and the water molecule around the negative ion. Do you see how in the water molecules that are surrounding the positive ions that the red oxygen is surrounding the positive ion, and over here it's the hydrogens that are more attracted to that negative? That's really fascinating, and we're going to come back to that idea as we start to learn more about the structure of water, because what we're going to learn when we draw something called Lewis structures later on is that the oxygen has a partial negative and the hydrogen has a partial positive. So if you have a negative ion, of course your negative ion is going to want to hang out, by the partial positives, and your positive ions are going to want to hang out next door to the partial negatives. Don't let this sign right here freak you out. That's just the lowercase symbol for delta, which means partial. So let's contrast this to something that's not ionic, molecular, or covalent compound. Just to make sure, molecular and covalent actually mean the same thing, but people are starting to update their terminology, so don't freak out about that. So this is probably super hard to see, but inside this there is a sugar molecule, and so the sugar molecule, we'll just draw a little blob, an oval blob to be general, because a sugar molecule is something like C6H12O6, depending upon the type of sugar you're referring to. And so this sugar molecule just gets completely encased by all the water molecules, right? And if you want to add those little guys on there to show the hydrogens. And so your sugar doesn't have a charge to start with, right? This is not a charged molecule. Actually, all molecules are not charged. Only ionic compounds contain components that have charges. So originally what happens is the sugar molecules just kind of sit next to one another like this when they're solid. And then the water molecules come in and they kind of migrate over to the sugar molecule. They attract themselves to the right spots, and then they pull this guy away from his friends and then surround it in water. And so that's what it looks like when you are trying to draw the picture of an ionic compound versus a molecular compound dissolving. So let's talk about how this is going to relate to things that we care about. Okay, so let's see. First, let's make sure that we can answer these two questions. What type of compounds dissociate into ions when they dissolve? And you know what? Let's go ahead and answer this one first. What does it mean to dissociate? Dissociate means to break apart. So then we can come back to this question and say, what type of compounds break apart into ions when they dissolve? Okay, so your sugar molecules, covalent compounds, they don't contain ions. Ionic compounds contain ions. So ionic compounds, when they dissolve, break apart into their smallest component, which is ions. Whereas molecules will just break apart into the individual molecules. So make sure that you can kind of look at that picture that we just went through and label those components. So let's relate this to electrolytes now. So first, we should probably define what an electrolyte is. So an electrolyte is something that is going to conduct electricity. So when we start talking about electrolytes in chemistry class, these are going to be solutions that contain ions, because it's the ions that allow the electricity to be travel from one side of the, oh gosh, my brain's failing me. What are these things called? Not probes. What are they called? Cathode and anode. Do you know about cathodes and anodes? I don't know. How about complete the circuit? I think that everybody knows about completing the circuit. So the ions in the solution would travel through the water to complete the circuit. If you've ever had an opportunity to actually do something like this, and you can stick those into vegetables, that's pretty cool. Because if you stick it into a potato, the potato actually has enough ions in it and water to conduct the electricity. It's super awesome. So this one is more, physicsy, and you might be hard to see on your black and white, but this light bulb is the one that has the greatest amount of light coming through it. And if we kind of look down here to what that light bulb is trying to, I guess what that solution is, what is in that solution, what we see in comparison is we have no ions to a handful of ions, which means we have some lighting up of that light bulb, to many ions, and then electricity is really successfully conducted. So one of the things that's a common misconception is, let's write this down over here, is that water is a good conductor of electricity. And that's false, because water is a molecular compound. Molecular compounds don't conduct electricity well. It's the ions in the water that are doing the conducting. So as we start to talk about this idea of conducting electricity, we also need to cover, oops, goodness, I went too far. Oh, no, I didn't. when an ionic compound is going to conduct electricity. So basically, the idea of solubility. And this question right here is like that density question that people ask you of like which one's heavier, a pound of gold or a pound of feathers. That's the version here in solubility. So will an ionic compound that is insoluble in water create a solution that conducts electricity? So that's a big nope, because things like marble are ionic, but if they don't dissolve in water, they don't create ions, and so they can't conduct electricity. So let's talk about this idea of solubility, right? Because we just said insoluble. So solubility means that something can dissolve in a solvent. And so we can take this idea of solubility and apply it to all kinds of locations. So if we look at soluble compounds, which is what we're going to do next, these things dissolve in water. They are often seen as something called spectators in metathesis reactions. And we can report things that are soluble with respect to a concentration. For example, lead ion is soluble in water. And so if lead is soluble in water, then when we start talking about the Flint water crisis, we can report that in concentrations of parts per million and decide if it's high enough concentration to be a lethal dose, or at least poison you. So then the other thing is we can also focus on insoluble compounds. And if something forms an insoluble compound, these are going to be solid in water. These are going to be called precipitate, which we're going to abbreviate as PPT during chemical reactions. And we can collect that at the end and figure out its mass. So during the course of a reaction, we could collect the precipitate, and then that'll give us some idea of how much of the reactants were present. So let's look a little bit about solubility, and then we'll wrap up this first video. So for the solubility rules, I am going to reluctantly give you these. And I say reluctantly given because on the final exam, they will not be given. But I think there's just too much information on exam 2 to also expect you to kind of have an idea of what things are soluble and what things are insoluble. So you're going to have this table on exam 2, but that doesn't mean that you know automatically how to use it. So we've got a question here, and let's work on it. So we want to figure out if these compounds that are listed here are soluble in water. So let's start with lithium hydroxide. Oftentimes, there are two ways to solve these questions. You could either look at the lithium or you could look at the hydroxide, and both will get you to the right answer. So let's pretend we're looking at hydroxide. So we find the hydroxide in our table, and we see that this is something that generally forms insoluble compounds. And then we check the exceptions. And if lithium is an alkali metal, then this is not going to be insoluble, but rather will be soluble. So you certainly need to know that the alkali metals are group 1. Don't get that confused with the alkaline earth, which is group 2. Completely different. So make sure you keep those straight. So let's do magnesium hydroxide. Again, we find hydroxide. Magnesium is not listed here because magnesium is an alkaline earth element. And of course, magnesium is also not ammonium, calcium, barium, or strontium. And so this is going to stay true, and it's going to be insoluble. Let's look really quick how we might have also used the other direction. So for magnesium, there's no other place in here that magnesium is listed, but for lithium, there is. See how over here it says alkali metals group 1A? Always soluble, no exceptions. And so if you would have looked at lithium first instead of hydroxide, you would have gotten to the same answer. So let's finish up with our last two. Barium carbonate. So I see carbonate right away, and I see that that's on our list over here. Barium, not an alkali metal. Barium is also not ammonium. So if the carbonate is present in the insoluble part of the table, then that means that we have an insoluble compound. If barium was over here in the exception list, then we would switch from insoluble to soluble. Let's look at our final example. I see chloride right off the bat. And notice how chloride is up here in our soluble table. So chlorides generally make soluble compounds, but then you have to come over and you have to double check the exceptions. So lead is indeed an exception, which means that you take the idea that chloride makes insoluble compounds, and if lead's an exception, you flip this from soluble to insoluble. If you want to tack on one more example, something like barium chloride, that would be soluble because chlorides tend to form soluble compounds. Barium is not an exception. So we're going to practice this a bunch more in class because sometimes it can seem so straightforward that people don't practice and then they find out way too late that they really didn't understand it in the first place. So we're going to stop here for now, and we'll pick up with a second video on another section of this chapter. So as always, thanks for your attention, and this is Katoni signing out.